We use one cell in an electric circuit to understand the concept of EMF and internal resistance of a cell. We will now look at different combinations of cells and conceptualize an equivalent EMF and equivalent internal resistance for these combinations, just as we did in the case of resistors in series and in parallel combinations. Cells are connected either in series or in parallel combinations to obtain the required voltage and current in a circuit. To calculate currents and voltages in a given circuit, the combination of cells is replaced by an equivalent cell that gives the same EMF as that of the combination. First, let us consider a combination of two cells that are connected in series. One terminal of each cell is joined together, leaving the other terminals of the two cells free. There are two ways to make a series combination of two cells. In the first way, the negative electrode of the first cell is connected to the positive electrode of the second cell. In the second way, the negative electrode of the first cell is connected to the negative electrode of the second cell. Let us now analyze the first case, where the negative electrode of the first cell is connected to the positive electrode of the second cell. E1 is the EMF of cell 1. R1 is the internal resistance of cell 1. E2 is the EMF of cell 2. R2 is the internal resistance of cell 2. The potential at point A is VA. The potential at point B is VB. The potential at point C is VC. VAB is the potential difference between points A and B, which also represents the potential difference between the positive and negative terminals of the first cell. We know that terminal voltage V is equal to E minus I into R. Substituting the corresponding expressions of cell 1 in this equation, we can now write VAB is equal to E1 minus I into R1. Let this be equation 1. Similarly, for the second cell, we can write VBC is equal to VB minus VC is equal to E2 minus I into R2. Let this be equation 2. We can now write the potential difference between the terminals A and C of the combination of cells as VAC is equal to VA minus VC, which is equal to VA minus VB plus VB minus VC. Substituting from equations 1 and 2, we have VAC is equal to E1 minus I into R1 plus E2 minus I into R2. Rearranging and simplifying the right side of the equation, we have VAC is equal to E1 plus E2 minus I into R1 plus R2. Let this be equation 3. Writing equation 3 in the form V is equal to E minus I into R, we get VAC is equal to EEQ minus I into REQ, where EEQ is the equivalent EMF and REQ is the equivalent internal resistance of the combination of the cells. Let this be equation 4. Comparing equations 3 and 4, we can write EEQ is equal to E1 plus E2. Let this be equation 5. REQ is equal to R1 plus R2. Let this be equation 6. Equation 5 is used to calculate the equivalent EMF of the series combination of two cells. Equation 6 is used to calculate the equivalent internal resistance of the series combination of two cells. Let us now observe changes in the equations when the negative terminal of the first cell is connected to the negative terminal of the second cell and E1 is greater than E2. Let us call this case 2. We will now proceed with the derivation just as in case 1. As E1 is greater than E2, current I leaves the positive terminal of the first cell, goes through the external circuit and moves from the positive terminal of the second cell to its negative terminal and finally reaches the negative terminal of the first cell. The current leaves the second cell from its negative terminal. As the direction of the current I within the second cell is opposed by its EMF E2, E2 is taken as negative in the equation for VBC. Hence, we get VBC is equal to minus E2 minus I into R2. Let this be equation 2. Writing the equation for VAC. By substituting equations 1 and 2, simplifying and putting it in the equivalent form, we get EEQ is equal to E1 minus E2. Let this be equation 5. From equations 3 and 4, we can write REQ is equal to R1 plus R2. Let this be equation 6. We can now extend these rules to any number of cells in a series combination. Rule number 1. The equivalent EMF of a series combination of n number of cells is the algebraic sum of their individual EMFs. If, in the combination, the current leaves any cell from the negative electrode, the EMF of that cell will bear a negative sign. Rule number 2. The equivalent internal resistance of a series combination of n number of cells is the sum of their internal resistances irrespective of the orientation of the terminals of the cells in the series combination. Let us now consider a parallel combination of two cells. The positive terminals of the two cells are connected to each other. Similarly, the two negative terminals are connected to each other. I1 is the current leaving the positive electrode of the first cell. Similarly, I2 is the current leaving the positive electrode of the second cell. At junction point B1, I1 and I2 flow in and flow out as I into the external circuit. At any point in a circuit, the total charge flowing in must be equal to the total charge flowing out. So, at junction point B1, we can write I is equal to I1 plus I2. Let this be equation 1. VB1 is the potential at point B1. VB2 is the potential at point B2. the potential difference between points B1 and B2 taken across cell 1 can be written as V is equal to VB1 minus VB2. V is equal to E1 minus I1 into R1. Rearranging the terms, we can write I1 is equal to E1 minus V divided by R1. Let this be equation 2. Similarly, taking points B1 and B2 to be across cell 2, we can write V is equal to VB1 minus VB2. V is equal to E2 minus I2 into R2. Rearranging the terms, we can write I2 is equal to E2 minus V divided by R2. Let this be equation 3. Substituting equations 2 and 3 in equation 1, we get I is equal to E1 minus V divided by R1 plus E2 minus V divided by R2. On simplifying and rearranging the terms, we get I is equal to E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. By further rearranging the terms, we can write V is equal to E1 R2 plus E2 R1 divided by R1 plus R2 minus I into R1 R2 divided by R1 plus R2. Let this be equation 4. We can replace the combination of two cells with one cell of EMF, EEQ, and internal resistance, REQ. We can now write V is equal to EEQ minus I into REQ. Let this be equation 5. From equations 4 and 5, we can write EEQ equal to E1 R2 plus E2 R1 divided by R1 plus R2. Let this be equation 6. REQ is equal to R1 R2 divided by R1 plus R2. Let this be equation 7. Equation 7 can be written as 1 by REQ is equal to 1 by R1 plus 1 by R2. Let this be equation 8. Dividing equation 6 by equation 7 and rearranging the terms, we get EEQ divided by REQ is equal to E1 by R1 plus E2 by R2. Let this be equation 9. In the circuit that we used, two positive terminals are joined to each other, and similarly, two negative terminals are joined to each other, and currents I1 and I2 are flowing out of the positive terminals. If the negative terminal of the second cell is connected to the positive terminal of the first, equations 8 and 9 are still valid by replacing E2 with minus E2. Equations 8 and 9 can be extended when n cells of EMF E1 to En with internal resistances R1 to Rn are connected in parallel combination. They can be replaced with a single cell of EMF EEQ and internal resistance REQ. We can write 1 by REQ is equal to 1 by R1 plus 1 by R2 plus and so on up to 1 by Rn. EEQ by REQ is equal to E1 by R1 plus E2 by R2 plus and so on up to En by Rn. Most electric circuits are made up of a number of resistors and cells interconnected in a complicated way. The formulae that we derived for series and parallel combinations of resistors and cells are not sufficient to determine all the currents and potential differences in such circuits. Kirchhoff's rules are used to analyze these complicated electric circuits. Rule number 1. Kirchhoff's first rule is also called Kirchhoff's point rule or Kirchhoff's junction rule or nodal rule. This rule is based on the principle of conservation of charge. At any node or junction in a circuit, the sum of currents flowing into that node is equal to the sum of currents flowing out of that node. This rule can also be expressed as the algebraic sum of currents in a network of conductors meeting at a point or node is 0. The current entering the junction is taken as positive, and the current leaving the junction is taken as negative. This statement can be expressed mathematically as sigma Ik. K ranging from 1 to n is equal to 0. Rule number 2. Kirchhoff's second rule is also known as Kirchhoff's loop or mesh rule. The algebraic sum of changes in potential around any closed loop involving resistors and cells in the loop is 0. The electric potential at any point in a closed loop depends only on the location of the point in the loop. So, starting from any point in the loop, if we come back to the same point, the sum of potential changes must be 0. ABCDA is one of the closed loops in a complicated circuit. Starting from any point in the loop, we walk through the loop either in a clockwise or anti-clockwise direction and write down the change in potential. Let us start from point A and walk through the loop in the clockwise direction. That is, ABCDA. And note down the change in potential. AB. While moving from point A to point B, we go from the negative terminal of the battery to the positive terminal of the battery. Therefore, the change in potential is plus V, which is the voltage of the battery. BC. Current I1 is passing through R1. The direction of current I1 and the direction of walk-through is the same. The change in potential is minus I1 into R1. Here, you should clearly understand why the change in potential is minus. Charges always flow from a point at higher potential to a point at lower potential. Therefore, point B is at a higher potential compared to point C. We are calculating the potential change between points C and B, which is the potential at C minus the potential at B. Hence, the change in potential is negative. CD. Current I2 passes through R2. The direction of I2 is opposite to the direction of walk-through. Current always flows from a higher potential to a lower potential. Therefore, the change in potential is minus of minus I2 into R2, which is equal to plus I2 into R2. Another way of expressing this concept is as follows. Here, charges are flowing from D to C. Therefore, point D is at a higher potential compared to point C. As we are calculating the potential change between points D and C which is the potential at D minus potential at C, it is positive. dA. Current I3 is passing through R3. The direction of I3 and the direction of walk-through is the same. The change in potential is minus I3 into R3. To apply Kirchhoff's rule 2, we add all these changes in potential and equate it to 0. Let us now apply Kirchhoff's rules to find the current in each branch of this complicated circuit. There are two important steps in the procedure. Step 1. We label and indicate the direction of current in each branch of the circuit. Next, apply Kirchhoff's first rule at every junction point. Step 2. We apply Kirchhoff's second rule to the closed loops in the circuit. The number of closed loops chosen depends on the number of unknown currents as per step number 1. Let us start with the branch AC for labeling the current and its direction. Current I1 leaves the positive terminal of a 10-volt battery. Therefore, the direction of current I1 is from C to A. Next, let us take the branch BED. Let us assume that the current I2 leaves the 5-volt battery from its positive terminal. Therefore, the direction of I2 is from E to B and D to E. The assumption that we have made for the direction of current I2 may be wrong. In that case, at the end of the solution of the problem, we obtain a negative value for I2. Then, we change the direction of I2 and write the answer. The three branches BA, CA and DA meet at the nodal point A. We have already labeled the current in branch AC. We have to now label the currents in the remaining two branches. Let us assume that a current I3 is flowing in branch BA in the direction A to B. We are now left with only one branch, that is, AD, to which we have to label the current. Let us assume that the current is flowing from A to D. We can now apply Kirchhoff's first rule to find the magnitude of this current. Next, let us take the nodal point B. Three branches AB, EB and CB meet at point B. The current in branches AB and EB are already labeled. We have to find the current in branch BC. Currents I3 and I2 are flowing towards point B. Therefore, the current in branch CB must flow out of the point. We now apply Kirchhoff's first rule to find the magnitude of this current. Next, let us take the nodal point C. There are three branches meeting at point C. Only the current in branch DC is not known. Let us assume that the current in this branch is flowing from C to D. We now apply Kirchhoff's first rule at node point C to find the magnitude of the current in branch DC. We have labeled the currents in all the branches. We have a self-check to see whether the magnitudes of the current in the branches that we calculated are correct. Let us apply Kirchhoff's first rule at nodal point D. As Kirchhoff's first rule is satisfied, the current in the branches that we have calculated is correct. There are three unknowns in the circuit. They are I1, I2 and I3. To find the values of these unknowns, we apply Kirchhoff's second rule to any three closed loops in the circuit. Loop ABCA. Let us start from the negative terminal of the 10-volt battery. Walk through the loop in a clockwise direction and add the potential changes. Substituting the values of the potential changes across the resistors and that of the cell in the loop and simplifying, we get equation 1. Loop ADCA. Let us again start from the negative terminal of the 10-volt battery and walk through the loop in an anti-clockwise direction. Add the potential changes step by step and equate it to 0. Substituting the values of the potential changes across the resistors and that of the cell in the loop and simplifying, we get equation 2. Loop ABCDE. Let us start from the negative terminal of the 5-volt battery and walk through the loop in an anti-clockwise direction. Add the potential changes and equate it to 0. Substituting the values of the potential changes across the resistors and that of the cell in the loop and simplifying, we get equation 3. We have so far obtained three simultaneous equations with three unknowns. On solving these three simultaneous equations, we get the values of the unknown currents as shown. Substituting these values, we get the current in the various branches as shown. The Wheatstone bridge is an electrical circuit shaped like a rhombus, ABCD. The four sides of the rhombus are made up of four different resistors, R1 to R4. Across the vertical diagonal BD of the rhombus, a galvanometer is connected to detect current. Across the horizontal diagonal AC, a cell is connected. I1 to I4 are the currents through the corresponding resistors R1 to R4. IG is the current passing through the galvanometer. Let G be the resistance of the galvanometer. The formulae we derived for series and parallel combinations of resistors and cells are not sufficient to determine all the currents and potential differences in such circuits. Let us now apply Kirchhoff's junction rule at junction points B and D. At point B, I2 minus IG minus I4 is equal to 0. Let this be equation 1. At point D, I1 plus IG minus I3 is equal to 0. Let this be equation 2. Let us now apply Kirchhoff's loop rule to the two closed loops, ADBA and CBDC. Loop ADBA. Across points A and D, by applying the rule, we get minus I1 R1 plus IgG plus I2 R2 is equal to 0. On simplifying, we get I1 R1 is equal to I2 R2 plus IgG. Let this be equation 3. Loop CBDC. Across points B and C, by applying the rule, we get I4 R4 minus IgG minus I3 R3 is equal to 0. On simplifying, we get I4 R4 is equal to I3 R3 plus IgG. Let this be equation 4. As a special case, the values of R1 to R4 are chosen in such a way that Ig becomes 0. Now, substituting Ig equal to 0 in equation 1 and simplifying, we get equation 5. Substituting Ig equal to 0 in equation 2 and simplifying, we get equation 6. Substituting Ig equal to 0 in equation 3 and simplifying, we get equation 7. Substituting Ig equal to 0 in equation 4 and simplifying, we get equation 8. Substituting for I3 and I4 from equations 5 and 6 in equation 8, we get I1 divided by I2 is equal to R4 divided by R3. Let this be equation 9. From equations 7 and 9, we can write R2 divided by R1 is equal to R4 divided by R3. Let this be equation 10. Equation 10 denotes the relationship between the 4 resistors for the galvanometer to produce zero or null deflection. This relation is therefore called the balance condition. The application of this balance condition is a practical method to determine an unknown resistance. Let us assume that R4 is the unknown resistance. R1 and R2 are known resistances. We gradually change the value of R3 till the galvanometer shows null deflection. The bridge now is in balanced condition, and we can apply equation 10. Rearranging the terms in equation 10, we can write R4 is equal to R2 into R3 by R1. Let this be equation 11. Equation 11 is used in a practical circuit, which is called the meter bridge. The schematic diagram of a meter bridge is as shown. A meter bridge consists of a 1 meter long standard resistance wire of uniform cross-section held taut between two ends of a metallic strip bent at right angles at the ends, placed alongside a meter scale. There are two gaps, one on the left and the other on the right. In the horizontal part of the metallic strip where two resistors, one of which is known and the other unknown, are attached. The end points A and C, where the wire is clamped to the metallic strip, are connected to the cell. One end of the galvanometer is connected to the midpoint B of the metallic strip between the two gaps in it. The other end of the galvanometer is connected to a jockey, which is a metallic rod with one end shaped like a knife edge. The knife edge end of the jockey slides over the wire to make electrical contact. R is the unknown resistance of a given resistor which we have to determine, and the resistor is connected across the right gap in the metallic strip. A standard resistance, S, in the form of a resistance box, is connected across the left gap in the metallic strip. The knife edge end of the jockey is moved along the wire until the galvanometer shows a null reading. Let D be the position of the jockey on the wire when the null reading is obtained. Let R be the resistance per centimeter of the standard wire. As the area of cross-section of the standard wire is constant, its resistance is proportional to its length. Thus, the resistance of the AD part of the wire is equal to R into L, and the resistance of the DC part of the wire is equal to R into 100 minus L. The Wheatstone bridge and meter bridge circuits are very similar. The table shown gives the comparison of resistances between the Wheatstone bridge and the meter bridge. As the current in the galvanometer of the meter bridge is 0, the circuit in the meter bridge is a balanced one, and hence we can apply equation 11 to the circuit. Substituting the expressions for the resistances in the meter bridge in equation 11 and simplifying, we get the expression for the unknown resistance R is equal to S into 100 minus L divided by L. Thus, we find the resistance of an unknown resistor using the principle of the Wheatstone bridge in a meter bridge circuit.